All right, so now we are being recorded, and everyone, thank you very much for coming for the second version of a DOTS seminar. We're really happy to have Sriram Sankaranarayanan. I, of course, butchered it, Sankaranarayanan.
Yeah, that's close enough.
Joining us today, and he's joining us from a different apartment in Montreal, but he's part of our Montreal crowd. He sits next to me in the office next to me. And I'm really happy to have him talk about some of his recent work on game theoretic aspects of when Nash meets Stackelberg. So take it away, Sriram.
Thank you, Alex, for the introduction. Today I'm going to talk about a specific form of game which is motivated from applications in the energy markets. And I'm going to present some theoretical and algorithmic results on these games. And if anybody has questions, I think you have a raise a hand feature in Zoom, and I guess I will get a notification. But otherwise, I'm not looking at anybody's videos, so I have no idea if you physically raise your hands.
And also, if you write in the chat, we will either let Sriram know if he doesn't see it, or he might see it there too.
Yeah, perfect. Thank you. So let me define what games are. Games are decision-making problems. We could have a single decision maker, and in that case, we call these problems as optimization problems. And the solution concept here is something called as optimal decision or optimal solution. On the other hand, we could have multiple decision-making multiple decision makers. In the sense, you could have multiple agents, which we call players, and one player's decision affects the payoff of every other player. And in this type of setting, which we call as a multi-decision maker game, the solution concept is what is called an equilibrium. And there are various definitions of equilibrium. And then I'll define some of the definitions which are relevant to this talk shortly. So in case of optimization, two broad classification as convex optimization or non-convex optimization. When we have this property of convexity, which refers to some set of U-shapedness of the objective, and it's a nice technical property. The problem is generally much easier to solve compared to a non-convex optimization problem where it could be much harder. And in decision-making problems, we have two broad categories: simultaneous decision-making problems and sequential decision-making problems. In simultaneous decision-making problems, as I said, there are multiple decision makers, and they all make a decision simultaneously. That means when each player makes a decision, they only have a belief about what everybody else's decision is going to be. Or in contrast to that, we could have a sequential decision-making problem where there could be one entity who makes a decision, then there could be another entity who observes the decision of the first entity and then retrospectively makes the decision. But the first entity, they anticipate how the second entity is going to react and decide in the first place. Again, even these decision-making problems, when we have multiple players who are making decisions, their individual optimization problems could be convex or non-convex. And in literature so far, the problems where the game theoretic problems where each decision maker's optimization problem is convex optimization problem, that has received significant interest, and that is primarily because we know good reformulation techniques where these convex games can be reformulated as a non-convex optimization problem. And since we generally have a very good understanding of the theory of optimization and solving at least certain types of non-convex optimization problems, like maybe integer programs or complementarity problems, these have received a lot of attention. But when the decision makers in a game, in a multi-decision maker setting, if each of their optimization problem is already a non-convex optimization problem, then the above said reformulation it is not possible to make such reformulations, and we need completely novel techniques to solve problems of this form. And in this talk, what I'm going to talk is a very particular form of non-convexity, and we will discuss about how can we find Nash equilibria for these problems. And now let me make the definition clear. When I say Nash equilibria in a multi-decision player multi-decision maker problem. It means given it is a set of strategies such that given everybody else's strategy, you can never be better off by changing your strategy. And this property holds for everybody. In the sense, once we are at a Nash equilibrium, no player will have a incentive to unilaterally deviate from the decision. They will stick to this decision. All right. So let me define a Nash game formally. I define Nash, this is exactly equivalent to the more common definition used in economics, but I'm stating the same in the following format just so it could motivate the following stuff more directly. So a Nash game is a tuple of optimization problems. Can somebody tell me if you're seeing my mouse pointer as I point it here?
Yep.
Okay. So a Nash game is a tuple of optimization problems such that the ith player optimization problem, the feasible set doesn't depend on any other player's decisions, but the objective function of the ith player is a function of the decisions of the ith player as well as every other player except the ith player. So this is where the game aspect comes in, because each player's objective affects everybody else's objective. This is a very well studied problem, and if little f is a convex function and the script f is a convex set, then we have good reformulation techniques, and there are multiple market models in this field of energy, food markets, etc., which solve convex Nash game and use the solution hence obtained for policy research. This is a standard simultaneous game. Then there is sequential game, where we have typically 2 players, but can easily be generalized to more players, where we have a first mover player whom we refer to as leader. Here, the leader's decisions in this problem are referred to by the variable x. The leader first decides the variable x, and given the decision of the leaders, the follower, if it is a single follower, they solve an optimization problem. If it is multiple followers, they all play a Nash game, and you get a solution to that optimization problem or a Nash game. And this can be seen, a good motivation for this is you can see the leader, which is the first mover, as maybe a country or a government, which is imposing taxes and certain rules for trade inside the country. And once the tax structure and the market rules and characteristics or mechanism is decided, the players in the market, which could be individual producers, etc., they could play a Nash game to obtain a Nash equilibrium. So each of these players among themselves, it's a simultaneous game, but they are sequential to the leader. They observe the leader's decision first. And now if you look at the problem of the government, it should be as following, such that the government now wants to decide the tax structure and the rules of the game such that the government's objective is maximized. The government's objective could be something like public welfare or curtailing carbon dioxide emissions, anything at all. And these games are generally harder to solve than Nash games. There are few models which use it, but it is still used in practice. So this block diagram shows how the Stackelberg games work. The leader is the first mover, and once the leader sets their decision, which affects each of the follower and also the rules of the game, the followers are engaged in a Nash game. All right. Now the question we ask is, what if there are multiple leaders and each have their personal set of followers? The motivation behind this game is the following. So consider a similar country as the leader and the producers, maybe the domestic producers of energy as followers setting. Now you could have each country trying to curtail emissions, but not compromising on GDP, etc. But different countries can also trade energy with each other. They can get into agreements with with each other. And in this interaction between countries, we want a Nash equilibrium. So let me reiterate the point. So given the tax and the policies of a country, the followers are playing a Nash game. The country and its own personal set of followers are playing a sequential or a Stackelberg game. And different countries, the governments of different countries, they are engaged in a Nash game with each other. And this is what we refer to as Nash among Stackelberg players. And that motivates the title of the talk, When Nash Meets Stackelberg. This is a type of game which reoccurs multiple times in literature, subtly showing its face, but as far as we know, we have not seen this defined formally. So we gave the name NASP. So the questions we ask for this problem are, so given an instance of a NASP, which means if I give you the optimization problem of each of these countries and each of the followers of the country, does this problem always have a pure strategy Nash equilibrium, or does this problem always have a mixed strategy Nash equilibrium? Or if it always doesn't exist, can we compute can we find when does it exist, and if it exists, can we compute the Nash equilibrium? These are the fundamental questions we are asking in the context of these games. So the first answer for, is this problem very hard? Yes, the problem is not very easy. So if we have to say that formally, we characterize the computational complexity of these games. So we state that it is sigma p too hard to decide if a given instance of trivial NASP has a PNE. And when I say, I think, did I skip this? Okay. When I say trivial NASP, it refers to a problem with exactly 2 leaders, and each leader has exactly 1 follower, and everybody's optimization problem is a linear programming problem. So linear as in continuous linear programming without any integer variables at all. And given the setting, this is the simplest problem one could come up with. And we show that it is sigma p too hard to decide if this problem has a pure Nash equilibrium. And it's also sigma p too hard to decide if the problem has a mixed strategy Nash equilibrium. Pardon the typo, this should be an MNE, not PNE. So, and by sigma p too hard, what do I mean? Suppose I am given a NP oracle, which means suppose somebody can tell me I can solve NP hard problems instantaneously, then I'm going to ask this person's help exponentially many times, which in other words, any algorithm that finds the existence of PNE or MNE, that's pure strategy Nash equilibrium and mixed strategy Nash equilibrium for these games, necessarily makes 2 raised to 2 raised to n elementary operations, where n is the bit size representation of the problem. There is one consoling fact though. If there are finitely many leaders, and if each leader has exactly 1 follower, and if every player's feasible set is bounded, then there is a reduction to finite games, and we can show that a mixed strategy Nash equilibrium always exists. So the decision problem aspect goes away there. But what we don't know is what if we have 2 or more leaders, and even if we have more than 1 follower per leader. The third point here, it necessarily requires 1 follower for each leader. If we have more than 1 follower, we still are not sure about the complexity class of those problems. I'm not going to walk through the proof of this theorem. It has a nice construction, and the proof is available in the archive version of the paper. But right now, I'd like to spend more time in the actual algorithm, which we'll use to solve these problems, which means we are going to do 2 raised to 2 raised to n elementary operations, but we are going to find whether a PNE exists and MNE exists or not. So for the algorithm, we work with the following assumptions. So we allow multiple followers for each leader, and we no longer require that each player solves only a linear program. We can actually extend it to a convex quadratic program, but the constraints are all affine constraints. And as we said before, the followers can play a Nash game with each other. So among leaders, again, we can have multiple leaders. So there is no interaction between the follower of one leader to a follower of another leader. For example, a producer in the US cannot directly talk to a producer in Canada. The interaction goes only through the governments. And if we are interested in mixed strategy Nash equilibria, we need that each leader solves a linear program. I mean, apart from these bi-level constraints and interaction terms, except for that, what we need is a linear program. But if you are happy with, if you only look for pure strategy Nash equilibria, then we are happy if the leader just has a convex quadratic program. And the interaction terms are all bilinear terms. You can multiply the variables of one leader with the leader variable of another leader. That's allowed. All right. So one result which motivates the algorithm in this talk is a result from one of our earlier papers, which says the following. So consider feasible region of a Stackelberg game, as we decided before, as we defined before, which means you have some polyhedral constraints and some variables y. This should be a solution set of some other Nash game, which is parameterized in x. You can again think of x as the leader's decisions, which is the country's or the government's decisions, and y as the follower's response. Then this set is basically a finite union of polyhedra. And in fact, the other direction also holds, in the sense every finite union of polyhedra can exactly be described in this form, which says we cannot, say anything sharper than just saying that this is a finite union of polyhedra. This is useful because our understanding of polyhedra and their geometry is relatively more than our understanding of just bi-level games in themselves. And as I said, we cannot do much better because every finite union of polyhedra could be described this way. But there is a catch here. I say this is a finite union of polyhedra, but it can very easily be exponentially many polyhedra. And in most cases of interest, it actually happens to be growing exponentially fast. So this is one theorem. Please keep this in mind. I'm going to recall it shortly. But let me also say, why is it slightly harder to solve these problems as opposed to regular optimization problems? So imagine you have an optimization problem, a non-convex optimization problem. Let the region that you see here in yellow be the feasible set of your optimization problem. Let's say you have a convex outer approximation for this problem. Now, what does this tell me? If I solve an optimization problem over this convex outer approximation, then that optimal value serves as a bound for my original optimization, non-convex optimization problem with this yellow feasible set. This means, this means this outer approximation is giving you useful dual bounds, and a tighter and tighter outer approximation could give you more and more useful bounds. And analogously, if you have an inner approximation, as shown in orange here, if you optimize over this orange set, then that gives a primal bound for the optimization problem over this original non-convex region. This is again useful because, if you once find a feasible point for this orange in this orange set that's also feasible in this yellow set, well, and very trivially, infeasibility of this blue outer approximation implies infeasibility of the original problem in yellow, and feasibility of the inner polyhedron orange implies the feasibility of the set in yellow. But all this logic becomes very, very less useful when we are talking in terms of finding Nash equilibrium problems. In the sense, if you have an approximation of, even a very good approximation of the feasible region, existence or non-existence of Nash equilibrium for these approximated versions could mean nothing at all to the original problem. To motivate this, let me give you an example. So consider this problem. It's just a two-player problem. Both solve a linear optimization problem. The first player's optimization problem is the first player's variable is x and second player's variable is z. Now look at what is going to be the Nash equilibrium. Nash equilibrium, I say it's going to be 1, 1. It's a pure Nash equilibrium because, x is always going to take a positive value, which means the second player's optimization problem is just to minimize z, and the smallest value of z that they can take is 1. And fixing z equal to 1, the smallest value of x we can obtain is again 1. So 1, 1 is a pure Nash equilibrium. But consider this problem where the second player's feasible region is not 1, 5, but a union of these two intervals. So you could think of this in either way. This problem, which we talked about first, you can consider that as an inner approximation of the second problem, or you can think of this problem that we are talking second as the outer approximation of the first problem. Either way, it doesn't matter. But all that we showed is the inner approximation has a solution, pure Nash equilibrium, which means if you are thinking purely from an optimization perspective, probably the outer approximation, the bigger set, the one with the bigger set, should also have a solution. But we'll show that the second problem doesn't have any Nash equilibrium at all. Let's see why. So observe that players 1's variable x necessarily takes a positive value because of this constraint, of course. So, but if you fix that x is any positive value, then the players 2 player 2's optimal solution is decided, which is necessarily going to be the smallest value of z that you can assign it, which is going to be -5. But once you fix the second player's optimal solution as -5, the first player's problem is unbounded, which means you give me any x, I'm always going to be able to give you a better solution for player 1. So effectively, this problem doesn't have a Nash equilibrium at all. So the problem with a larger feasible set ended up not having a Nash equilibrium. And you can also easily show if a problem has a smaller feasible set, the same kind of the same effect can happen. So the inner and outer approximation don't necessarily provide existence guarantees. So what is our hope? Let's try to exactly understand the feasible set first. All right. So as we know from the other theorem, we can say that the feasible region is a union of some polyhedra. Let this be what you see in blue here, be the feasible region of the first player. And similarly, what you see in green be the feasible region of the second player. And just for understanding, this is a polyhedron, generally a very high dimensional space, and every point here that you see colored is a combination of the three things, which is a leader strategy, which means in the context of country, it's maybe a tax policy of a country. And given the tax policy, it also has the follower's response, for a follower's optimal response, given the leader's tax policy, and also a dual certificate that the follower is actually responding optimally. So each point here, so we at least have three terms already, but this is a two-dimensional space, but I cannot show higher dimensional figures here. But the idea is the same. Each point here corresponds to a leader strategy, a follower decision, and an optimality certificate for the follower. All right. Well, one good thing that we know is that this is a finite union of polyhedra, and polyhedra are objects that we know to deal well with, which means there is a Balázs formulation which helps in finding the closed convex hull of this finite union of polyhedra. It's going to be a humongous task given that there are exponentially many polyhedra. But for a moment, let's say we can find the closed convex hull of this union of polyhedra using Balázs equation. Now for a moment, forget this original polyhedra which gave these convex hull. So now all that you have is two polyhedra, which are the convex hulls of the original problem. And you could have some convex objective function that we had right from the beginning. Well, now this is a convex game. What you're seeing right now on the screen, this is a convex game. And using our good old techniques, we can find Nash equilibrium for this convex game. Or, we can show that no Nash equilibrium exists. But let's say we find a Nash equilibrium. Oh, I'm getting some message in chat. Oh. Okay. So this is a Nash game. Well, let's see if the Nash equilibrium obtained for this convex game happens to be feasible for the original problem. So in case of player 1, we turned out to be lucky. It's a feasible point in the original problem. But for the player 2, it appears in the convex hull, but it's not originally feasible for any of the polyhedra. But again, given that it is a point in the convex hull, we can write it as a convex combination of some set of strategies. In fact, if you are in n dimension, at most n+1 strategies using Kara theory. Well, so let's say this red point here, the equilibrium is x star. You can write it as, as a convex combination as shown here. But look at this eta. These are all positive numbers which sum to 1. And what we show now is these weights in the convex combination can actually be interpreted as probabilities in this formulation. So let me say the statement more formally. Let me state the statement here first. So playing this strategy in the convex hull is equivalent to playing each of these three strategies with the probability equal to the weights assigned in the convex combination for these strategies. And what we show is this is always true. It's a theorem that we rigorously show, where if you rewrite any strategy in the convex hull as a convex combination, then you can actually consider each of the individual strategies in the convex combination and the convex combination weights as pure strategies and probabilities, and what you end up always happens to be a mixed strategy. And we also show the result in the other direction, which means every mixed strategy Nash equilibrium can always be written in this form, which means if your convex game that you obtained in the previous slide did not have a Nash equilibrium, then the original problem doesn't have a Nash equilibrium either. All right. I'd like to talk about some notable features. So what we do is in the complete enumeration at the end of it to find these individual strategies and the Nash equilibrium for the convex game and all this step is we show that it can be written as a mixed integer linear problem, a feasibility version of the MILP. So this immediately gives a lot of good news because, you know, as and when solvers like Gurobi or Cplex improve, if you can solve these MIPS faster, then that directly improves our code. We can find Nash equilibria faster. And, you know, we also have a small tweak to the algorithm, which I don't want to go into due to lack of time, such that you can force that you are only looking for pure Nash equilibria and not mixed Nash equilibria. It's just a few more linear constraints and binary variables. Basically, you have to set those probability variables as only one among them should be non-zero. And what if you want all the MNEs or all the PNEs for the problem? Well, since we give the entire problem as a MIP feasible problem, enumerate all the solutions of the MIP. And if you get all the solutions of the MILP, then they correspond to all the MNEs and all the PNEs. So sometimes it might be the case, there are different Nash equilibria, and you might want to select a Nash equilibrium which maximizes the welfare, or you want to analyze what is the worst Nash equilibrium is. Well, we had a feasibility version of the MILP MIP that we presented earlier. Now maximize or minimize the same objective over the same feasible region, and you get the appropriate best MNE or worst MNE, best PNE or worst PNE. And we can also show another thing. If we are only interested in two-player zero-sum games, then it's not even a mixed integer program. We actually return a linear program. And, you know, the sigma P2 result doesn't hold for zero-sum games. But, you know, if we have a zero-sum games, then we can be way more efficient. And in the leaders, even if we want to add nonlinear constraints like second-order cone constraints, they are easily amenable. You add a corresponding constraint to this original MIP, and you should be able to obtain Nash equilibria. So due to lack of time, I'm going to skip the refinement of this algorithm, which proposes an iterative approach instead of enumerating all the polyhedra right in step one. But I'm happy to discuss about this sometime else. And the future work that we are working on is, you know, to develop an equivalent outer approximation algorithm. And I did not talk about the inner approximation. I skipped it, so it's probably not enlightening. But, you know, despite the problem about inner approximation and outer approximation that I spoke originally, we observed that, you know, it could still give some push to our algorithm. It can guide our search better. And another question is, what if we have some stochasticity in the leaders and followers problems? You know, instead of writing each of these optimization in the complete extensive formulation, can we do something smart to solve these problems? It's because, you know, these problems are are of interest in the energy sector, where stochasticity is a very important component due to expansion of renewables and whatnot. And we are also thinking about extending this work if the leaders have shared followers, which means there are two leaders and the followers respond to both their decisions. And we are also planning to apply this to energy policy analysis. Thank you. I leave it there.
Thank you very much, Sriram.
Sure.
Let me just turn on my video again. And now we have some time for questions. So if you have questions, either you can raise your hand virtually and we will unmute you, or you are free to write the question in the chat and either Sriram or I will read it out to you. Sriram, I'll let you field the questions if there are any, and we'll give a few minutes for that.
Sure.
Hey, Sriram, I have a question about the computational results.
Mm-hmm.
So can you say more about the difficulty of the instances you generate? You mentioned that you leverage existing MIP solvers. Do they struggle? Are those easy problems? Do you wish you could solve larger versions, or in reality, will people need to solve larger versions? Can you say a little bit more about that, please?
Yeah. So in reality, yes, we'll definitely need to solve larger versions. And you can really see how this sigma p2 complexity is killing us. If we, so right now we can solve something like 5 countries and 3 energy producers in each country. We can solve that in something like 5 hours. And then let's say we add something like 1 more producer in 1 country, then it suddenly shoots up to something like 50 hours. So we are trying our best to even formulate the problems as concisely as possible, maybe pre-solving it, but still we get interesting results that you couldn't have just guessed by looking at the problem. The Nash equilibria seem to be enlightening.
But the increase comes from the fact that you need to solve more MILPs, not that the single MILP is bigger, or is it?
No, the single MILP is also much bigger.
Okay. Okay.
Single MILP is,
Okay. Thanks.
Sure.
So Sriram, I was thinking about that theorem that you have with the showing that in certain cases it's sharp p hard, sigma 2p hard to figure out whether a PNE or MNE exists. But you said that when the feasible regions are bounded, then you can do, then certainly an MNE exists, right?
And exactly 1 follower per leader.
And exactly 1 follower per leader. Yeah. Okay, but it also requires this assumption that the feasible region is bounded.
Yeah, definitely.
Okay, and so if you have an unbounded problem, and let's say you take a truncation of the feasible region, some kind of inner approximation, right? Now by that, and if it's in one of these problems where there's exactly 1 follower, now you have a bounded problem, so you know an MNE exists. And now if the MNE is in the interior of this bounded region, then that means that there's also an MNE for the original problem, right?
True.
Okay, and is there any way to leverage that, make that useful?
I am not sure if this could be made useful, but what I have noticed is if the original problem, the unbounded problem, doesn't have an MNE, and if you artificially put bounds, then you almost always get strategies at the bound.
Well, that's the converse of what I was saying, right?
Yeah,
so then
exactly.
if it's on the boundary, that means that expanding it, it's kind of like saying, oh, hey, we can improve in that direction. Okay, so yeah, that's kind of what I was thinking about, of trying to handle the unbounded case in some way. I don't know.
Okay.
Okay, so are there any other questions from the audience? You can also ask questions after the talk. There will be some time for a tea or coffee, in which there will be breakout rooms in which Sriram and Gabriele and other co-authors who are here, I think Margarita and Andrea might be here too, and that they will be able to be in that room and answer some questions if they want. And also there's a Discord channel that's on our website that you can ask questions about the talk throughout the week and after the week as well. So I guess with that said, let's thank Sriram again.
Thank you.
And I'm going to stop the recording for Sriram's part of the talk and start it again for